Hi, my name is Howard, and I'm here to talk to you about the root and the ratio test.
Well, that's it for my intro, as I'm a bit unhinged by the camera. Because some of us are humorally challenged, we cannot make perfect intro videos like some of our compadres. Before we begin, there are a couple of tricks that will help in solving these root and ratio problems. The first we will look at involves exponents. Exponents of the same base can be combined with their exponents being added, as such. 2 squared times 2 squared is equal to 2 raised to the 4th. This is because the base combines into 1 and the exponents add. Similarly, they can be taken apart in the same manner. 1 over x raised to the n plus 1 is equal to 1 over x to the n times x. The next involves factorials. The factorial symbol is denoted by an exclamation sign and simply means to multiply the number by every previous whole number before it until you reach 1. For example, 5 factorial would be equal to 5 times 4 times 3 times 2 times 1. But it can be rewritten as 4 plus 1 factorial. 4 plus 1 factorial can be rewritten as 4 plus 1 times 4 factorial, because this, in essence, creates 5 times 4 factorial. The last one involves a fraction being divided by a fraction. In this case, 1/5 is being divided by 2/4. Because of the keep, change, flip rule for dividing fractions, we are going to keep the first fraction, change the symbol from division to multiplication, and flip the second fraction. The same can be done for series. If a of n is equal to 1 over n, and a of n plus 1 is equal to 1 over n plus 1, then when you divide a of n plus 1 by a of n, you can flip a of n knowing that it will have to be flipped. Let's start with an easier problem. In this example, we have the summation from n equals 1 to infinity of 1 over n factorial. First, we can see a of n plus 1 is equal to 1 over n plus 1 times n factorial. A of n is equal to 1 over n factorial. If we take the limit as n approaches infinity of a of n plus 1 over a of n, we have 1 over n plus 1 times n factorial times n factorial over 1. The n factorials will cancel out, leaving you with the limit as n approaches infinity of the absolute value of 1 over n plus 1. If you take the limit, it goes to 0. Because of the ratio test, the series converges. This problem has n raised to a power, and the first thought might be, can I use the root test? Looking closely, the root test is determined to be undesirable because the limit as n goes to infinity of the nth root of n factorial is not readily known. Therefore, the ratio test is more suitable for this problem. A of n plus 1 is n plus 1 times n factorial over 3 to the n times 3. A of n is n factorial over 3 to the n. Taking the limit as n goes to infinity of the absolute value of a of n plus 1 over a of n results in n plus 1 times n factorial over 3 raised to the n times 3 times the reciprocal, which is 3 to the n over n factorial. Close the absolute value. The result is the 3 raised to the n canceling and the n factorials canceling, leaving you with the limit as n goes to infinity of n plus 1 over 3, absolute value, which is equal to infinity. Therefore, by the ratio test, the series is divergent. With this problem, using the ratio test will be a lot easier to solve for convergence or divergence. A of n plus 1 is n plus 1 over 4 raised to the n times 4. A of n is n over 4 raised to the n. If we take the limit as n goes to infinity of the absolute value, we get n plus 1 over 4 to the n times 4 times 4 to the n over n. The 4 to the n's will cancel out, leaving you with the limit as n goes to infinity of the absolute value of n plus 1 over 4 times n. If we take the limit of that, we can see that the coefficient of n in the numerator and the denominator make 1 over 4, so the limit is 1/4. Because 1/4 is less than 1, the series. These next few problems get a little bit more complicated. For this problem, we will be using the ratio test, and we can see adding 1 to the numerator produces n plus 1, all cubed, which you will see in a little bit that they do not readily cancel out. A little algebra is needed for this problem. Let's start by writing out a of n plus 1 and a of n. A of n plus 1 is n plus 1, all cubed, over 4 raised to the n times 4. A of n is n cubed over 4 raised to the n. We need to take the limit, so we write the limit as n goes to infinity of the absolute value of n plus 1, all cubed, over 4 raised to the n times 4 times 4 raised to the n over n cubed. The 4 to the n's will cancel, but the n cubed and n plus 1 cubed do not readily cancel. You have to expand the binomial in the numerator, but you do not have to expand it completely. As you can see, when you expand it, you get n squared plus 2n plus 1 times n plus 1. Now, the n squared and the n plus 1 make an n cubed. The denominator has the highest degree as n cubed. That means the other parts to the binomial are not necessary. But for algebra's sake, we will complete it. Simplifying, we have the limit as n goes to infinity of n cubed plus 3n squared plus 3n plus 1 over 4 times n cubed. If we take the limit of that, we just need to look at the coefficients of the highest degrees, which is 1 over 4. That means the limit of this is 1 over 4. Since 1 over 4 is less than 1, the series converges. This problem seems really complicated, but once you start doing it, it becomes easier. First, write out a of n plus 1 and a of n. A of n plus 1 is n plus 1 times n factorial over n plus 1 raised to the n times n plus 1. A of n is n factorial over n raised to the n. We need to take the limit, so we write the limit as n goes to infinity of the absolute value of n plus 1 times n factorial over n plus 1 raised to the n times n plus 1 times n raised to the n over n factorial. As you start to cancel out, you realize that the n plus 1's cancel and they are on the same fraction instead of canceling across. This leaves you with the limit as n goes to infinity of the absolute value of n raised to the n over n plus 1 raised to the n. The bottom is always going to be 1 above the numerator, so the limit as n goes to infinity is 0 and the series converges. Now we have a situation where n is an exponent to something, but nothing else. For this problem, using the root test is recommended. The conditions for convergence and divergence remain the same with regards to limit behavior. No more having to write a of n plus 1 and a of n. Instead, you write the limit as n goes to infinity of the absolute value of the nth root of a of n. For this problem, we have the nth root of 1 over 5 raised to the n. which simplifies to the limit as n goes to infinity of the absolute value of the nth root of 1 over the nth root of 5 raised to the n. The nth root and the n as an exponent cancel, as radical 2 squared would cancel. For the nth root of 1, it will always be 1 no matter what number you use. Simplifying leaves you with the limit as n goes to infinity of 1/5. Taking the limit of this leaves you with 1/5, which is less than 1, so the series converges. There are series where the root test is the best and the easiest test to use for the problem. Take this problem for example. You would have to spend a lot of time figuring out n plus 1, which means every single n would have plus 1. And then you would have to divide, and that is another set of complications right there. So the root test will simplify this. Take the limit as n goes to infinity of the absolute value of n. We have the nth root of n over 2 plus n raised to the n. Right away we can see that the nth power is cancelled out by the nth root. This leaves you with the limit of a regular look-alike, somewhat sort of not really like a function. We have the limit as n goes to infinity of n over 2 plus 1. As n goes to infinity, the coefficients determine the limit since the degrees of the highest exponent are equal. And since the limit is 1/2, the series converges due to the root test. You can now infer that the root test is especially useful in problems that have n raised to a power and that is the only variable to consider. In this next problem, it is evident that using the root test will benefit us greatly, but there is a pi thrown into the series. But fear not, even though pi is never ending, it is still a constant and will be treated as such. Since we are using the root test, we can just write out the stuff that we've been writing for quite some time now. Yeah, nth root of that, blah, 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 blah. Okay, the nth root and the nth power cancel. That leaves you with the limit as n goes to infinity of 2 pi over 3. But wait, that is a number that you don't know. I mean in decimal form, of course. But we know pi to be approximately 3.14. Fantastic. So we multiply that by 2 since it's in the numerator. That gives you 6 point blah 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 divided by 3, which is 2 point blah blah blah. But 2 point blah 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 is still greater than 1. So because it's greater than 1, it diverges because of the root test. Now that we've gone over examples that make finding the convergence or divergence of a series quite simpler than before, you might be wondering, why don't I use this all the time? This is like magic. This example is one of many that show these two tests' weakness when the limit is equal to 1. Dun dun dun. So we're going to start with the ratio test for this problem. And we know a of n plus 1 equal to be 100 over n plus 1. And a of n equal to 100 over n. Well, if you take the limit as n goes to infinity of a of n plus 1 over a of n, you have 100 over n plus 1 times n over 100. The 100s cancel, but the limit of n over n plus 1 doesn't exactly equal something less than or greater than 1. It equals exactly 1 because of the coefficients. And then that's a sad face. So we go to the root test to find some salvation, but you have the limit as n goes to infinity of the absolute value of the nth root blah 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 of this test, and you kind of sit there and then you look at it and you realize you don't know the limit as of the nth root of n, and you sit there kind of sad as you finish writing the problem because you don't know it, and then that's another sad face. So you know, sometimes these two tests don't work, and then you cry. Sad face.